Welcome back to my quest to see if I can make benzene from vitamins. In the last video I synthesized aniline from vitamin B12, and now I'm going to run some tests to see what I can do to convert that to benzene. And finally, I'll scale whatever works up. Now that I've made aniline, I'm going to run some experiments to see the best ways to knock this group off of the ring. The general path I'm going to take is to diazotize this with nitrous acid, made in situ from an acid in sodium nitrite, leaving me with a benzene diazonium salt, which should be much easier to reduce than the aniline directly. There's a whole class of reactions that do this called Sandemeyer reactions. Now, the most common way to reduce this is with something called hypophosphorus acid, which is supposed to work great, but has two crucial problems. One, it's hard to get because it's Schedule 1 in the US, and two, it decomposes into the horribly toxic gas phosphine. So that's a non-starter as far as approachability for the amateur goes. So let's explore some other options. Poring over some random papers and scrounging up ideas myself, I've got 4 candidates for reducing agents. First, vitamin C. Second, isopropyl alcohol. Third, sodium metabisulfite, here his stump remover. And fourth, surprisingly, chloroform. I'm pretty hopeful about sodium bisulfite. It sounds pretty good from the papers. It's surprising to me that chloroform could work at all, but we'll see how that goes. Interestingly enough, reducing these salts with alcohols goes all the way back to 1864, although pretty inefficiently. But teasing out a bunch of info from a bunch of different papers, I think isopropyl will give me a good shot. Although it likes to form an ether where it just replaces this nitrogen with the oxygen from the alcohol and forms this big molecule that I don't want at all. And finally, we have vitamin C, which I haven't heard anything about, but it's a mild reducing agent and it would be super cool to be able to make benzene from 2 different vitamins. Once we've run all these tests, we'll analyze them with a method called thin layer chromatography, which can be used to see if any of these actually make benzene by comparing it to a standard. In this case, benzene I made from the traditional benzoic acid route. So let's get to it. Here are my first solutions to try. I'm going to be doing isopropyl alcohol and vitamin C, and we'll see how this goes. So I've weighed out the powders. Now I just need to go ahead and dilute them up with water. This will be the sodium nitrite. This is sodium acetate. This will be used to help push the isopropyl reduction to make what I actually want as opposed to the ether. This is vitamin C, just exactly the vitamin that is in oranges, etc. Here it's a nice white powder. Here's isopropyl alcohol, already weighed out. And these will be our 2 reaction test tubes. So this is just water right now, but it's got a tiny little stir bar in there. And now we'll go ahead and dissolve the aniline and make aniline bisulfate by adding some sulfuric acid. So let's get these stirring, as both adding sulfuric acid to water is exothermic, but also deprotonating the aniline to make aniline bisulfate is also exothermic, and so good mixing will be important. Cool, now we can add the aniline. A lot of that is just crashing out of solution, so I'm gonna have to have water to knock it back down. Got a good amount of crystals of aniline sulfate. Cool. As these dissolve, we got to start cooling these, since this the diazonium salts will decompose above 5 Celsius, and so we'll get these going on an ice bath. Now that the sodium acetate is dissolved, I'll go ahead and actually just pour this into the isopropyl alcohol solution, as that's the reaction it'll be part of. And now we just wait for this to cool down and we should be good. All right, so we got all these solutions cooling. Once they're at 5C, we'll be good to go.
this is, right now this is just aniline bisulfate in water. No difference in these tubes, but the aniline bisulfate does not like staying in solution. Then we got the isopropyl alcohol, and I'm going to need a bigger tube for this. Yeah, definitely. And the sodium nitrite, and soon we'll be able to mix these up. We've made it to 5 Celsius, and now we can go ahead and add the sodium nitrite solution. No visible change, is to be expected. Cool, now that the vitamin C is dissolved, we'll also get that in there. This is already cold, so nothing's stopping us from adding the isopropyl alcohol. I don't expect any obvious change, but we'll see. Immediately became pretty yellow. This might actually be because of the formation of isopropyl nitrite. Yellow is pretty characteristic of nitrites. But we'll get that stirring. We'll call that cold enough. Wow, instantly very yellow. Who knows what that is? Cool, we'll stir those for a bit, and then we'll replace this ice bath with a water bath, and we'll heat it up to around like 60 Celsius for a few hours. We'll see. This is mostly just a qualitative test, see if I get any appreciable amount of benzene. Oh, pretty interesting though. Something's precipitated out in the isopropyl one. Oh, and that's definitely some nitrogen. Yeah, bubbles of nitrogen in the isopropyl one. Interesting. That's pretty cool. So this one's definitely working, depending on what that means. Like, a Sandmeyer reaction is happening, and we'll see if that's replacing it with what I want. The paper I'm following, the yields were still only like 40%. The rest was the ether. But we'll see how this works. The vitamin C, there's a couple bubbles. So we'll see. Maybe this just needs to rise to a higher temperature. But hey, that's science. All right, we've got this swapped to a hot water bath. Yeah, it's like actually right in the perfect range. Let's get these in there, and we'll see what happens. Got these stirring. Lots of nitrogen evolution here. That's pretty cool. Lots of nitrogen evolution. Well, it'll be pretty interesting if we get like an organic layer. That's cool. Well, something's happening. Could just be decomposition to phenol. The diazonium salt will do that when heated, but hopefully not. These have been going for a bit over an hour, and there's no more nitrogen production. There is... Oh, they've really changed colors, but let's go ahead and turn this off and take a look. Here's the isopropyl one. As you can see, it's dark brown, and also it's separated into 2 layers, which is pretty interesting. This bottom layer is likely the organic layer, simply because it is a smaller amount. You can see it's separated there. And it's heavier than water, which is interesting. Benzene's lighter than water, so we'll see what that is. Plenty of junk, hence the brown. Here's the vitamin C one. No obvious separation of layers. So we'll dilute this down, perhaps pop in a separatory funnel to see if we can coax it to. And in the meantime, we can get the next test going. Here, I have a mixture pre-made. This, where the actual hydrogen donor is chloroform, so that'll be interesting. And this one, the reducing agent will be sodium bisulfate. So I've already mixed most of these up. The only thing to add is the sodium nitrite, and then the bisulfite has a separate solution. And these apparently are just supposed to be at room temperature. So we'll get these stirring. Here's the sodium nitrite for the chloroform. That's the only ingredient. Instant color change. Then the sodium nitrite for the bisulfite solution. Also immediate color change. I would expect these to decompose quite quickly. Like, this is not at 5C, but the papers I'm following has it at room temperature. And then finally, here is sodium bisulfite, which goes in the bisulfite tube. Another nice color change. Well, now I'll add a bit of water to each of these tubes to make sure I got everything. Tons of nitrogen evolution in the bisulfite one. All right, there we go. Crank that to maximum. Lots of generation here. Yeah, this one's mixing really poorly. I might just need to get that in a beaker with a better stir bar. I think I'll do that. All right, now let's check out our results. Bisulfite is looking pretty good. You can see the organic layer, tiny bit at the bottom. So that's hopefully benzene. I think it probably is, honestly. Looking at the other ones, well, the chloroform one became quite a beautiful tar. Just a disgusting.
It's tar. Play the test.
I don't think that's the one we'll be scaling up. Here, looking back at the vitamin C one, no sign of an organic layer anywhere, so that's not a good sign. And then the isopropyl, there's a decent section at the bottom. That is organic. Cool. What we're gonna do is we're gonna extract each of these. This one, the bisulfite's looking the most promising, that's for sure. At this point, we're gonna extract these with some hexanes, and then we're gonna run some thin layer chromatography to compare it to a source of what I know is benzene, to see if we actually made any. So here we have the results of our runs, just like loosely separated using hexanes. On the left, we have the isopropyl and then the vitamin C, and there's the organic layer. That's mostly hexanes. And on the right, we have the bisulfite and the chloroform and the organic layers. I had to add some extra hexanes to the bisulfite to get it to actually group up at the top. And, well, now we'll run some TLCs and we'll see what we get. All right, we've got some benzene from sodium benzoate, the typical like dry distillation, super high temperature method that's popular with amateurs. And we're gonna run a TLC to compare it to some of these extracts. First, we'll do the isopropyl and vitamin C.
A TLC starts with a simple glass plate with silica fused to it that I spot a couple samples on. Then, I dip it into a solvent and let capillary action pull it up to cover the plate. As it flows through my spots, it'll actually separate the compounds in them based on their polarity, since the silica substrate is polar and my solvent, hexanes, is nonpolar. Then, I can compare my tests with my standard benzene to see if I made more benzene. The only problem here is benzene is super volatile, and so actually working fast enough to see the spots is nearly impossible. Even keeping everything generally in the freezer was just barely enough to kind of work. Anyways, for the ones where the benzene did stay long enough, the silica on these plates is treated with something that fluoresces in shortwave UV, and benzene blocks shortwave UV. And so I can shine this light on it and then circle the dark spots so that I can see where things ended up once it is all evaporated.
Cool. As you can see, it looks like we did make benzene with the isopropyl alcohol. Vitamin C, none. Isopropyl alcohol, of course, made a bunch of other things, but a distillation is pretty likely to split those up. Also, I'm amazed at how few spots my benzene from sodium benzoate had. Like, it really just had one spot, so that's cool. Yeah, pretty good. All right, let's try the other two.
Then, just like that batch, I ran TLCs against the other ones, as well as a couple conformational tests of the isopropyl. This was super frustrating, as it was just so hard to tell if I was getting real results or just seeing things with how fast the benzene evaporated. In the end, though, I felt like I was getting pretty reproducible results, and the reduction with isopropyl alcohol looked the best. So now, all that's left to do is to give it a try at a large scale. To scale this up, I'll largely just do what I did before, which was inspired from a footnote on a table in a paper on this from 1958. So I had to get a bit creative to reproduce it at even a small scale, so we'll see how this goes at a bigger scale. First, I'll set up an ice bath and make the aniline hydrochloride salt.
Yeah, this is nice and cold. .1. Dissolve it, got a nice white fog. We'll have to wait for that to get back down to temperature. Then we'll add the sodium nitrite. All right, we're down to 5C. Now we can add the sodium nitrite solution. Cool. On that addition, we now should have dissolved the benzene diazonium salt. Let's see. Oh man. This got hot. I added that way too fast. So this is definitely actively decomposing. But we'll let that cool down. Yeah, that'll cut up to 25. So this is definitely decomposing. I see gas generation, so this is lowering our yield. But we'll get it back cooled down. So now we should have benzene diazonium chloride plus decomposition products, which will mostly be phenol and nitrogen. But this is cooling down very slowly. All right, well, my isopropyl is in the freezer, so honestly, I think it'll help cool this down. In the meantime, I'll add the sodium acetate. This will buffer the solution. The sodium acetate is very wet, but that shouldn't be a problem. It's a deliquescent salt, which means it'll dissolve enough water from the air to literally dissolve itself into a pool. And it's doing that for sure. Now we'll measure out the isopropanol. This has been in the freezer, so that'll help bring the temperature down a little bit. Yeah, that brought it down to 10C pretty quickly. Cool. Now, I'm actually going to de-gas this, since oxygen is pretty detrimental for the formation of the product we want. So I'll turn on my vacuum pump. And we'll see how much oxygen we can get out of solution. Looks like some, but there wasn't a ton in there, so that's good. All right, we'll call that good. Turn the vacuum pump off. And we'll keep it covered with some plastic wrap to keep air from getting back in. Or at least limit it. And then I have some argon, which I'll bubble through the solution to purge any remaining oxygen. And also fill the flask with argon, which is heavier than air. Now, we can slowly bring it up to temperature. Hopefully it didn't already decompose. But we'll take it out of the ice bath and slowly bring it up to 50 or 60 C for a few hours.
I ran this until there wasn't any nitrogen production, which in this case took about 2 hours, then took it off heat and let it cool down.
All right, now we can separate it. So I don't see an organic layer, but isopropyl alcohol will dissolve organics. So we're gonna have to add some hexanes and some water to help it split. Rinse it out with some water. Oh wow, it's already separating. That's cool. This is probably water. Wow. Rinse out the flask. I'm very interested to see what these products are, because this is supposed to be super dirty. So we'll see how that goes. And then some hexanes to help pull out the benzene. All right, then we'll shake this up. This looks pretty good. Actually looks like what I'd expect, definitely. So we have an organic layer on the top, a water layer on the bottom. And the organic layer is definitely quite dirty, both layers are. Cool, we're gonna wash the water layer a couple times with hexanes, try to get all the benzene out of it. This is actually still a little cloudy, so I'll wait a little bit longer for it to settle. But we have pretty different densities, and so these are separating nice and quickly. All right, drain the water layer. Now the organic layer. Cool, now I'll wash the aqueous layer with some more hexanes and put a little more water in there and really try to extract all of the benzene out. Because benzene is a little bit soluble in water, and especially with some alcohol in there. Now cap, shake, and vent. Drain the aqueous layer. Now we can just combine the previous organic layer. And this we're going to wash a couple times with a brine solution. This will pull out any more water and alcohol. Give that a shake. It looks like the grime is mostly soluble in organics. We'll drain off the water. Give it one more wash. All right, these are separated. Here's the organic layer. Now I'll add magnesium sulfate to dry it. And just add a random amount, really. You can see we got some big clumps, which shows that there's a good amount of water in it. But we still have some free-flowing powder left, which means that we should have gotten all the liquid, all the water out of it. Now we can add it to this flask for fractional distillation. We'll decant the first bit off. Now we've got this set up for fractional distillation. Here's the organic layer that we separated out. It goes through a Vigro column. This helps separate close boiling fractions. We definitely need this since the hexanes they put in there boil at 69 Celsius, while the benzene itself boils at 80. So that's quite close. Then it goes in here and we have a thermometer to make sure we can separate the right fractions. Heads into our condenser and then our receiving flask. We'll be swapping this out once we hit 80 Celsius. Right now we've just turned it on, so we're just chilling here at room temperature. Condenser water is a nice 3 degrees Celsius, so that'll definitely separate things out. All right, now I'll wait for this to come to temperature. This we'll want to do pretty slowly so that we can separate things properly. And I might need to insulate this column. We'll see if stuff comes over. Now we've got pretty vigorous boiling in here, and we can see the vapor front traveling up. There's the vapor front right there. All right, with our first drops of distillate. This is a really quite a cold temperature, but we're collecting still pretty quickly. So turn down the heat a little bit. All right, so we're definitely in the boiling point range of hexanes. Still collecting.
But soon we hit 80C, and so I swapped out the flasks.
Now we have our fraction coming over. It's crystal clear. This should be benzene. I've insulated the column to help get the last bits over. Boiling points slowly coming back down. I think we've exhausted the benzene and we just have higher boiling products. Yeah, this is going to come a lot down because this is likely like the ether, which actually I have very little of. But the ether boils very high. Yeah, so we'll let the last couple drops come over, then we'll stop it and analyze what we got. And here we have our fractions. Here's the first fraction. Lot of liquid. This came over between 40 and 70. Here came over between about 79 and 82, so should be almost exclusively benzene. Of course, it's a tiny amount. And this is what stayed in the boiling flask. Nice, tarry liquid. All right, let's run some TLCs. Let's see how these go. And we'll also see if we made any benzene. On the right side is the standard, which is the benzene from sodium benzoate. And on the left side is the ones we just made from aniline. I'll process this and hope it didn't all evaporate. My standard is not nearly dilute enough, and this benzene's definitely dirty. All right, I'm gonna dilute up the standard and we'll try this again. Nice. Pretty similar. So I feel confident we made benzene. It's definitely dirtier though. So for this route to actually be used, you'd want more purification steps. But given the yield, like, so the biggest, it's already, like, let's see if we can see it at all. No, it's already, a little bit. It's evaporating, but you can see it a little bit. But this is the biggest dot, and this matches perfectly with the standard. The standard's actually very clean. I'm surprised how clean the standard is. And then we do have a couple more polar impurities in there. But overall, I'm pretty happy calling this benzene. We got 6.1 grams, which is actually a 78% yield, which is great. So honestly, this is all in all, like there's a lot more steps but you get benzene. You don't need a crazy contraption to dry distill sodium benzoate. You can do it from aniline. So that's pretty cool. And there we have it. 6.1 grams of benzene. Boils at about 80 Celsius. Smells like benzene. TLC reveals a couple impurities, but overall pretty pure, matches the standard. I'll count it.
Overall, I'd say this went pretty well, and with some tuning, could be a useful additional option for the amateur to make benzene. If I were to do this again, I'd add the sodium nitrite solution much more slowly to the aniline salt to reduce the decomposition I got then. I'd also definitely use less of an insane excess of isopropyl alcohol, as then I don't think I need to use another non-polar solvent in order to extract the benzene in the workup. I could just add water to get the layers to separate. Hexanes in particular can form an azeotrope with benzene, and that can both reduce our yield and dirty our final product, so it'd be great to avoid. But with how useful aniline is as a general feedstock, making a big batch of that to then make some of it into benzene is just useful. If you need benzene for a reaction, give this a try. Super curious to hear how it works for folks. And with that, thanks for watching. I have a bunch of projects planned with the aniline and benzene I made in these videos, so stay tuned and consider subscribing to see more. And a special thanks to my patrons, especially the premium and VIP patrons listed here. See y'all next time.